Welcome to Lecture 7 of Symmetries, Particles and Fields. So we continue the discussion of representations. There are a couple of ways in which representations are combined commonly to make new ones. And so we're going to discuss those ways today. We'll also discuss a topic, the topic of symmetries in quantum mechanics. And we'll finish off with an application of, in terms of one of the ways of combining representations in the So3 case. Okay, so there's a new section and it's going to be called Making New Reps from Old. New representations from old ones. So there's a really simple way of making new representations, and that's just to take the complex conjugate, because all of the group properties, etc., will follow if you complex conjugate them. So if DG is a rep of the group, then the complex conjugate is 2. And in fact, you can check by complex conjugating the relevant properties of the Lie algebra that its complex conjugate is 2. Representation, and the complex conjugate is called the conjugate rep. Representation, and it comes with its own associated conjugate representation space. So we'll call this new bar, which is, so if nu was the original representation space, new bar is the complex conjugate of it. So there's a few definitions associated with this. If the representation is equal to its complex conjugate, so this is the case in the So3 examples I've been giving, then the representation is called real. And in that case, the two representation spaces are equal. If we have that the conjugate rep is isomorphic to the original one, but isn't equal to it, then that representation is called pseudo-real. Pseudo-real representation, and in this case, the representations spaces are just related by the presence of this this invertible n by n matrix, invertible square matrix S. Now, the same goes for elements of the Lie algebra. So you also get pseudo-real representations of the Lie algebra. Okay, So we can actually combine representations in a couple of ways to make new ones. So let's take representations of the Lie algebra. We'll call them D1 and D2 with dimensions N1 and N2 respectively, and representation spaces V1 and V2 respectively. Then we have a definition of the direct sum. Of the two reps, and it's written with a plus sign and a circle. So this is the direct sum is this circle plus. And what this means is that we form an N1 plus N2 square matrix, which has D1 and D2 down the diagonal and zeros elsewhere. So this is N1 plus N2 by N1 plus N2. So this is for all x in the Lie algebra. So simultaneously, there has to be some transformation that we can make such that that is the case. So this, and there's an exercise in the book to take you through this. This is a representation of the Lie algebra itself. So this direct sum is that you can prove is a representation. And if you follow the exercise, you'll do that. And the representation space of this thing is written V1 direct sum V2, and it's just, you just write the N1 length vectors first in a column vector and the N2 length vectors in the second one. And so the dimension of D1 direct sum D2 is N1 plus N2. Okay, now, again, you'll be showing in the exercise that the block diagonal structure survives exponentiation for this direct sum. And so D1G plus D2G, where these are the exponentials of the little d1s, this is defined similarly. And it has the same representation space. So from now on, we're going to deal with reps of the Lie algebra with the understanding that the result also carries through for the representations of the group. From now on in this section, we deal with reps of LG with the understanding that results carry through to reps of G. So via exponentiation. So a representation of the Lie algebra, so let's call it D of X, and its rep space V. These have an invariant subspace, so this is an important definition, invariant subspace. So it's a subset of the representation space if D of X times U is in U for all X in the Lie algebra and all vectors in this subset. Now, there are two trivial cases, and we're excluding those. So one is when big U is just the empty set, or the other one is when it's equal to the representation space. So excluding those trivial cases, you can have an invariant subspace. Why is this important? This is important because when you exponentiate and get the member of the group, some of the representation space will be untouched by group operations. So the group operations will mix up some of the representation space, but not other bits. On exponentiation, some of the rep space will remain untouched by group operations. In other words, for that part, dgu is u. So this is shorthand for d of g, u is in u for all g in g and u in u. So in physics, we need to, for physics applications, we need to keep track of these. So this leads to leading to the notion of an irreducible representation. So this is commonly shortened to IRRAP because it's a bit of a mouthful and takes a long time to write, and, so, we will call it an IRRAP of the Lie algebra. And this has no non-trivial subspaces, invariant subspaces. So in other words, when you do group transformation, everything gets mixed up. So a representation is totally reducible if it can be decomposed into irreducible pieces via the direct sum. So it's another definition. A rep is totally reducible So in other words, the representation spaces have a direct sum. So UI is a representation space. So DG acting on UI just gives you some of that, gives you back UI. and dg restricted to ui is an irrep. So what does this look like in matrix language? This means that there exists a basis for V such that simultaneously for all G, I should say for all X in the Lie algebra, D of X is block diagonal. So D of X is D1 of X, D2 of X, and so on. And that's just from the definition of the direct sum, really. And there are zeros everywhere else. So the matrices have got zeros here. So this we're going to define as the direct sum from I equal 1 to K of DI X. So the same goes for D of G, remember. So just to make it clear, D of G is D1 of G, D2 of G, all the way down to dk of G. And that, of course, just comes through exponentiation. So why is this important? And the fact is that in each UI, only the states within that UI are related by the group symmetry. And so those are the ones within each UI that have similar properties, but they might be different. So between U1 and U2, for instance, they might have different properties. So states in UI are not related to those in the different U's. So J not equal to I. So for example, if G acts on a Hilbert space, of all physical states, only those within an irreducible subspace can have similar properties. Okay, good. So now let's turn to symmetries in quantum mechanics for general groups. So let's consider a quantum mechanical system with different energy levels. So we're going to label these by E0, etc. And they're increasing as the suffix increases. So these, for some Hamiltonian, big H. Now, so I'm going to just discriminate operators here that act on Hilbert states. So the states of the system are elements of a Hilbert space. So we're going to call it curly H, which is the direct sum, n bigger than or equal to naught, of the individual Hilbert spaces where the Hamiltonian acting on a ket of our states gives us the energy level, particular energy level for all states in the Hilbert space of that energy level. Okay. So each energy level has its own Hilbert space, and the direct sum of them all gives you the total Hilbert space of physical states. So a symmetry transformation on the states well, we're going to have some operator U acting on those states. U is a map from the Hilbert space to the Hilbert space, is a unitary operator such that U, H, U dagger, so the Hermitian conjugate, is equal to the Hamiltonian. Why is that a symmetry? And that's, well, under a symmetry transformation, the inner product is preserved. So in other words, psi prime, phi prime is psi phi. So the brackets remain invariant and the energy is conserved. So this leads us to the notion of a conserved quantity in quantum mechanics. So this is an observable. Observables are Hermitian operators. So we're going to call the observable I hat. So the hat denotes the fact that it's an operator that acts on the states. And an observable is a Hermitian operator which commutes with the Hamiltonian. So then our operator U that we've introduced is the exponential of IS times this operator at this observable I. And S is real. Okay, so this U is a symmetry transformation. So if we have a maximal set of linearly independent conserved quantities, linearly independent conserved quantities. So we write this as a set I, 8. Now let's have a superscript A to label the different observables now, such that, well, each of them commutes with the Hamiltonian, and A is in 1, 2, up to D, let's say. So then the Lie algebra the group transformation is the span over the real numbers of I times this conserved quantity IA. A is 1 up to D. So this is defined, because it's a span over the real numbers, this is defined as a real Lie algebra. And the bracket, the Lie bracket, is the Lie bracket of the observables IA and IB. So now consider all possible symmetry transformations U which are of the form U is e to the x hat, where x hat is in this Lie algebra. Oh, I should have put, excuse me, I should have put a little suffix R to make it clear that it's a real Lie algebra. So these U hats, the set of all these U hats form a Lie group G. So this is compact since it's a subgroup of a product of unitary groups. Okay, so x hat commutes with the Hamiltonian for all x hat in the Lie algebra. And the Hn, the individual Hilbert spaces, are invariant under the action of G, or under the action of the Lie algebra. So each Hn carries a representation of the group, each Hilbert space. Corresponding to little d of the real Lie algebra, such that dn of u hat is exponential of dn of x hat, which is in the matrix. It's a matrix, square matrix of dimension Hn, and it's a matrix of complex numbers. So actually, the fact that it's unitary, Wigner proved that, and you're going to prove that theorem too if you follow the exercise in the book. So this theorem, if the transformation preserves the inner product, it must be unitary or anti-unitary. So let's give the unitary option first. So dn to the -1 of u hat. So the representation inverse is just the representation Hermitian conjugated. And it's the same thing as for the Lie algebra, of course, as well. Well, with a minus sign. Okay. So he actually proved that it could be anti-unitary as well, but this isn't the case that we'll be concerned with. All right, so this is Wigner's theorem, theorem 3.1, and you'll be proving it, and the exercise in the book takes you how to prove that. Sorry, yeah. Beg your pardon. All right. Theorem 3.1 that I wanted to mention is a finite dimensional unitary representation is totally reducible. This is the theorem that you'll be taking through in the exercise. Okay, good. It's not difficult actually. It's just it involves an algorithm with looking at the invariant subspaces and using some linear algebra and vector spaces. Okay, good. So we've seen the direct sum as a way of combining two representations or several representations to give another representation. But there's another important way, and that way is called the tensor product. This is another combination. So another way of forming an E-rep. So this one, we form a time symbol in a circle, D1 cross D2, from our representations D1 and D2 of the Lie algebra. So it acts on a representation space V1 cross V2. So this is defined to be, okay, so now little v1 cross little v2, where little v1 is in, let me put, should put sticks on these, is in the first representation space and v2 is in the second representation space, such that, okay, so d1 cross d2, direct product with d2, corresponding to the Lie algebra element x, acting on this v1 cross v2 is equal to the representation of the Lie algebra corresponding to the element x, acting on v1 cross v2 plus v1 cross d2 of x, direct product with v2. So what happens is, you know, d1 carries on acting on its representation space, and v2 on its, basically, and that's for all elements of the x of the Lie algebra. So let's choose a basis. So let's choose B1 is defined to be the set of all V1j, where j is 1 to n1. For the first representation space, let's say those are, that's a basis, and B2, let's call, so here the dimension of the representation might be different. So in general, we'll call it some different symbol, alpha, and this alpha ranges from 1 up to n2. So now we define a basis for the cross product of the two representation spaces. So this basis we're going to call 1 cross 2. So this is defined to be B1 cross B2, which is the same thing as V1j cross V2 alpha. And so the dimension of this thing is just n1, n2. All right, so let's take a vector in this cross product representation space, vector W, which is in V1 cross V2, with components. Let me write that out. Components Wj alpha in the basis. So we can write the cross product of the Lie algebra elements in terms of its components. Components. So d1 cross d2 of x. So the component in the direction I alpha j beta is equal to d1 of x. So we take the ijth entry of that representation, and we take the alpha beta element of the identity matrix, and we add this to the ijth element of the identity matrix and take the alpha beta element of the second representation. So we might write this in a shorthand notation as D1 tensor product with 1, and this would be 1 cross D2. So we claim that this is a valid representation of the Lie algebra, but it's got properties to satisfy to make sure it is. So an exercise in the book will take you through that. Or, well, you'll have to do the working, but it will ask you to do that. So we need this property that the representation corresponding to the Lie bracket is the Lie bracket of the representations. Now, there's an important lemma here. Theorem 3.1 implies that if D1 and D2 are unitary and finite dimensional, then D1 cross D2 is written as a direct sum of some other irreps. Let's call those tilde actually. So we will end up with some direct sum when we take the tensor product. So these are some of the computations that you have to do in particle physics involves precisely that, working out what the direct sum corresponds to from the tensor product of two representations. So what we're going to show you now is a tensor representation of So3. So this will exemplify some of the things we've been talking about. So hopefully you've seen some SO3 tensors. You'll have certainly seen a 3-vector, which is an example of an SO3 tensor. A scalar field is also a trivial example. So we may represent the representation space of a tensor product by multi-index tensors. So for as an example, let's take 3 cross 3. So 3 direct products with 3. So here we write an 2-index tensor, Tij, where I and j, and I'm going to use other letters, are in 1, 2, and 3. Seeing as we're in SO3. So the idea is under an SO3 transformation, we get each of these indices transforms with an R factor. So this transforms in the following way. So R we saw before when we were looking at SO3. It's this, we gave an explicit expression for Rij. We haven't derived it yet. That will come later in the next chapter. But anyway, you've got an expression for R from the previous chapter. So, okay, fine. So what happens is each index gets its own R factor. And it's you know, there's an implicit Einstein summation over these indices. So okay, now let's look at the part corresponding to the trace. So if we consider a part Tii, how does this transform under SO3? Well, we can write this, we can write this as delta Ki, delta Li, TKL. So under an SO3 transformation, this part goes to Rik, Ril, TKL. Okay, so this is equal to R transposed. So if I take the transpose, I switch the order of the indices on this first thing, and this is R transposed R. So if it's R is in SO3, or even if it's in O3, R transposed R just gives us delta KL. This is the identity matrix back. So we see that the trace part of the 2-index tensor is actually invariant. We get the same thing at the end after the SO3 transformation. So actually, this is precisely an example of an invariant subspace of the tensor product. It's the trivial representation, or the singlet representation, it's called. So Tii is an invariant subspace of the tensor product. The trivial representation, singlet, or that we can write it as 1, vector 1. So let's give it its own symbol. So let's label it by phi. So I'm going to write it in a particular way. we'll write the delta ij in, and this 3 is just a convention, and it's because in SO3 we're in SO3 we write a 1/3. It just saves some factors elsewhere, but you can use a different convention if you want. So this is it's also in SO3. This is called the scalar representation. So here, a special role is being played by this delta ij symbol, this Kronecker delta. And in fact, let's look and see how it transforms under SO3. Well, each index gets its own factor of R. And again, taking the transpose of this first R, we end up with delta ij. So this delta ij is invariant under the SO3 transformation, and indeed, because of that, it's called an invariant tensor. There is another basic invariant tensor in SO3. If we look and see how the totally anti-commuting symbol, epsilon ijk, transforms under SO3, well, we know each index gets its own factor of R. Now, this combination this expression on the right-hand side, if you remember your matrix equations for determinants, this is equal to determinant of R times epsilon ijk. Now, because we've got SO3, the determinant is 1. So we see again that epsilon ijk is an invariant tensor. Of SO3. All right. Now, so in fact, those are the two invariant tensor, basic invariant tensors, and we can build up other invariant tensors from using them. So higher rank invariant tensors. So okay, so we've already seen phi is an invariant tensor. 2, but we can build up higher rank invariant tensors using delta ij's and epsilon ijk products and sums. Okay, so what I want to do now is think of objects that we can form out of our initial 2-index tensor Tij, and these invariant tensors, and see how they transform. So an obvious thing we can do is to multiply Tij with epsilon ijk, and I'm going to call that combination VK. So the important thing here is what we'll see is that it's the unsummed indices that are important. And so summation over an index, as we'll see, kind of cancels out their effect in some, well, we'll see how it works. So for this, we get 3 R's for the epsilon, 2 for the t. So again, I combine this one and that one to get a delta LO. And I combine these two to get a delta MP, TOP times R, Kn, epsilon Ln. Okay, which is equal to R, Kn, epsilon Lmn TLm, which is just R, Kn, Vk. Once I substitute back in for Vk. So what happens here, after all the dust has settled, the fact that we've got one unsummed index means that actually that index itself only gets one factor of R. So what we've done is anti-symmetrize. This epsilon anti-symmetrizes over the two indices of this tensor T. So the anti-symmetric piece transforms like a vector. Because vectors just get one factor of this R matrix. So in its own invariant subspace. So we've identified an irrep. So this vector formed by this anti-symmetric combination is an irrep because it's a non-trivial invariant subspace. Okay, so now I can use the deltas to form another irrep. So what we're going to do is form the symmetric combination of under the indices of Tij. So this is defined to be a half Tij plus Tji. Okay, so I can write this in terms of Kronecker deltas. So under SO3, what happens to this is we get RKX, RLY, TXY times delta KI, delta LJ plus delta KJ, delta LI over 2, TXY over 2, RIX, RJY plus RJX, RIY so I can write this in terms of RIX, RJY, T with the symmetrization onto the T now. So I'm going to define this as Tij prime. So that's what Tij transforms into. So this shows us how irreducible representations can be formed. Well, I should say, all right, beg your pardon, just 1 second. So the traceless part, remember, hidden in this this piece, this symmetric piece is the trace, and that's its own invariant subspace. So if we want an irrep if we want to make an irrep out of this symmetric combination, we have to subtract out the traceless, the trace of it. So the traceless part of this, let's define this as Sij, which is T with the symmetric part minus a third delta ij t kk is an invariant subspace. And therefore, an irreducible representation of SO3. So what's the dimension of this? Well, the dimension of T with I and J symmetrized over, that's the dimension of a 3x3 symmetric matrix, which is 6. But we subtract 1 off from getting rid of the trace degree of freedom. So the dimension of this representation is 5. Now, let's go back to this vector. So I'll define the vector, the transformed vector in this way. So because this has one free index left over, we could have skipped all this intermediate calculation and realized that this free unsummed index just gets its own factor of r under the transformation. And the same thing here, basically we get the same thing. Each unsummed index here gets its own factor of r, summed appropriately. So it's an exercise in the book to show that these tensor representations are actually representations of the group. So we can now provide a full decomposition of our tensor. So Tij, remember this was 3 cross 3. This is equal to Sij, which is a 5, plus epsilon I jk vk. This is a 3, plus a third delta ij phi. This is a singlet. So we found our decomposition of our tensor product in this case. And so each of these fields we've defined here, the phi, the vk, and the Sij, they're irreps of SO3. And so we could use those instead to build some field theory. So example, let's take Sij. So we have 5 independent components of this. Let's take them to be real scalar fields. So they're really functions of x mu in the 5 representation as we showed above. And if we were to represent things in this way, our invariant Lagrangian would just be a half d mu Sij d mu Sij minus m squared over 2 Sij Sij minus lambda Sij Sij squared. So this is invariant under SO3. You can tell that because all of the indices are summed over, and it's an exercise to check it in detail. You know how the Sij transforms under SO3, and so you can check for yourselves that that is indeed invariant. So weirdly, it's the indices that play a crucial role in this. And that's true for general numbers of them and general groups. If you've summed over all the indices, then the result is invariant. But we'll write all that down at the start of next time. Thank you.